I'm Kenji Watanabe from University of Tokyo. As Mr. Kosaka kindly introduced, I have been the Associate Professor of University of Tokyo since 2018. And before that, I worked at the Railway Technical Research Institute, which is the central research institute of the Japan Railway for 18 years. So I'm feeling very happy to have such an opportunity to introduce about the geosynthetic reinforced soil structure, GRS, which was developed around 1990s to 2000 through the collaborative research between the University of Tokyo and Railway Technical Research Institute. So my presentation as the first presenter of today's webinar, I would like to introduce the history and the development of the GRS structure for the Japan Railway. So this is the content of my presentation today. There are 8 topics. So first, I would like to start with introducing the background. What was the technical issue around 1990? Is it okay? Yes, first topic. So this is showing the Shinkansen. Shinkansen is the high-speed bullet train. In Japanese, we call it Shinkansen. And Shinkansen is a backbone line supporting the nation's development. And the first Shinkansen was started operation at 1964, connecting between Tokyo and Shin Osaka. That is the first one. And then we extended to west direction and north direction. So the first one, 1964. This year is very important for us Japanese because on this year, 1964, first Tokyo Olympic was held in Tokyo. The first one, not last year we have the second Tokyo Olympic, but 1964 we had the first one. So we started the Shinkansen operation just 10 days before the Tokyo Olympic. So 1964 is a very memorable year in Japan. And now the total length in operation of Shinkansen line is more than 2,700 kilometers. So let's look at the first generation of Shinkansen. Tokaido Shinkansen opened at 1964. Let's look at what kind of structure type was used and what kind of track type were applied to the first generation of Shinkansen. This shows the length ratio of the different structure types of Shinkansen. So for the Tokaido Shinkansen at 1964, more than 50% of total length was constructed by embankment. So there's many technical problems. So one is long-lasting and large residual settlement. And the second problem was low stability against rainfalls and earthquake, because in Japan we have a lot of earthquake. So even until today, we have to do the maintenance, long-lasting maintenance, and it's extremely costly. So that is what we experienced in the first generation of Shinkansen, 1964. So the second generation of Shinkansen, Sanyo Shinkansen, this red line, and Jōuetsu and Tohoku at 1974 and 1982, the railway engineer changed the structure type. This is showing the structure type on the same figure. And for second generation, for Sanyo Jōuetsu Tohoku Shinkansen, RC viaduct frame structures and bridge and tunnel was applied in place of embankment, because we had a lot of negative experience on earth structures such as embankment for the first generation. So the railway engineer thought that it is better to change into the RC structure. But the problem was it was costly. Initial construction cost was become costly, 25% increase from the first generation. And of course, it is not environmental friendly where on-site soil from excavation of slope tunnel is available. So we cannot reuse such on-site soil because the main structure was the RC viaduct. And let's see what kind of track type were used for this first generation and second generation. For the first generation, 1964, ballasted track on embankment was mainly used. But the bearing capacity of the embankment was not very high. So that is the main reason why the ballast track is used, because we had to use the clay and low compacted controlled embankment. So settlement of ballasted track became very large after the opening. So I heard that such settlement is still ongoing. So we have to do the maintenance almost every day for the ballastic track. But for the second generation, we changed it to the slab track on viaduct. This is showing the typical picture of the slab track, because the slab track doesn't need so much maintenance, but it have to be constructed on the very stable structures. It is written here, shown here, continuous RC slab track. Of course, the initial construction costs become very high, become higher compared to the ballasted track, but large reduction of maintenance cost can be expected. This is showing compare the construction cost, maintenance cost between the ballasted track and slab track, and the maintenance cost become almost quarter, 1/4 by using the slab track. However, the slab track only allow very small settlement of subsoil. So, for example, it allow only 10 millimeter of settlement in 10 years in service, which is determined by the serviceability point of view. And it allow only 150 millimeter after huge earthquake. Even after the huge earthquake, we allow only 150 millimeter, which is decided by the restorability of the railway structure. So the question was, is it possible to construct slab track on earth structure? So the answer is it is possible, but if we use embankment for the slab track, of course embankment it have a very gentle slope, so land acquisition costs become very high, and maintenance work is still needed for the slope surface. For the slope surface, we need some maintenance. So in order to reduce the acquisition cost, it is better to use the retaining structures. But if we use this retaining structure, the construction cost increases significantly with the increase of wall height, and such conventional type retaining wall, the seismic stability is low. So that was the problem. So the technical issues around 1990 was that how can we construct an earth structure, which is the cheap structures, which is strong enough against natural hazards such as heavy rainfall or earthquake, and does not require much maintenance work or much land for construction. So that was a technical issue around 1990s. So the railway engineer at that time tried to apply the terre-armée method, which is the French technique, reinforced soil structures. And it was applied from the 1970s for Japan Railway, as you can see from this picture. But there are some several problems to use terre-armée method for the railway. First problem was corrosion of metal strip occurred by electric current, because for the railway, we use the electric current to control the signal, and electric current will flow in this rail. So this electric current causes a corrosion of the metal strip. That was the first problem, technical issue. And the second issue is no design method against large earthquake, because it is developed in France, where there is no huge earthquake. But in Japan, we have to design such railway structure against large earthquake. So that was the problem. So only a few kilometers was used for the Japan Railway terre-armée method. So Japan Railway started a new research development using geosynthetic from 1988. It was collaborative research between University of Tokyo and RTRI, Railway Technical Research Institute. So for the third generation of the Shinkansen, which is quite recent construction, 1997, 2004, and 2016, the structure type changed a little. In the third generation, there is a revival of soil structure, because by using the geosynthetic reinforced soil structure, which is the main topic of today's webinar, we can achieve the high performance and low construction and maintenance cost at the same time. Then, and of course, the stability of this GRS structure is very high, so the small residual deformation was achieved. So it is possible to use a slab track on the GRS structures, and it is highly stable against rainfall and flood and earthquake, and it is environmental friendly when on-site soil from excavation, slope, tunnel, etc. is available. Okay, then this is a summary of the 3 generations of structure for Shinkansen in Japan. In the first generation, more than half is constructed by embankment or conventional type retaining wall. So the problem was low stability against earthquake or heavy rainfall, and larger deformation and bumps behind the bridge abutment. So, when we use embankment, it occupied wide space. So the second generation at around 1972, it high cost and no use of excavated, so it is not environmental friendly. So in the third generation, since 2000, the railway engineer started to use the GRS retaining walls because it has a high stability against rainfall and earthquake and cost effectiveness in construction and maintenance. So that is the brief history and the background of the how we developed and apply the GRS structures. So in the chapter 2, let's see what kind of development was done around 1990s for the GRS retaining wall. This picture was taken at University of Tokyo laboratory test. The researcher is preparing doing some model test on GRS structure. The model height is around 60 centimeters, and he's doing the air pluviation to make the backfill soil. And he prepared various type of facing for the GRS structures. For example, the type A, it doesn't have any facing, and he changed the rigidity of the facing from small to the larger rigidity. And of course, there is a reinforcement model, geogrid model inside the backfill, inside the model from type A, type B, B, C, and D. And this is one of the typical result of the model test showing the load-bearing behavior. And as you can see, the wall became more stable as the rigidity of the facing increases. So the engineer realized that the rigidity of the facing is very important. And I should say, some of the model like B and C, the reinforcement on the wall is not connected, not fixed. But for type D, it was fixed. So the researcher also realized that the connection between the wall and the reinforcement is also very important. But it is just a small model test. So in RTRI, Railway Technical Research Institute constructed the full-scale test embankment at testing yard. And surprisingly, this test embankment still exists. So if you have a time, please visit to see this test embankment. They constructed two full-scale test embankment. One is constructed by sand and another is constructed by clay. And they perform the vertical loading test. And you can see some part, the GRS structure was constructed by the discrete panel, and some part it was constructed by the rigid facing. And inside the embankment was divided into several sections. Then what we found is that the wall became more stable as the rigidity of the facing increases. For this show, after the test, when we used a discrete panel, we found that some buckling occurred at the bottom part of the embankment. So we realized that rigidity of the facing is very important. And the geogrid, the second finding is that the geogrid should be connected firmly to the facing. So based on such model test and full-scale testing, we developed the GRS retaining wall called RR3R method, which means a reinforced railroad with rigid facing method. So there's a geogrid, geosynthetics inside the backfill, and it's having the continuous rigid facing, and the geotic style connected firmly to the facing. That is the most important point of these structures. And this is showing the history of GRS structure for the practical use. Then the research started at University of Tokyo 1982 and Railway Technical Research Institute from 1987. And before that, after that, the application of this new method was increased. And now the total length of this method is exceed 200 kilometers. And in Japan, we experienced many huge earthquakes, 1995 Kobe earthquake or several earthquakes, but no damage was reported for this RRR method. So it is very, it have a very high seismic stability. And this slide also shows the location of the GRS retaining wall. Total length is more than 200 kilometers. And this number shows the location of the GRS retaining wall. And we also apply this method not only for the retaining wall, but also for the bridge abutment, which will be another topic in my presentation later, and GRS integral bridge, which will be introduced by Professor Tatsuoka for the second presenter. So this number shows the position of the old GRS structure, and here it means that the GRS bridge number of GRS bridge abutment and integral bridge. So GRS structure have already become a very common railway structure, earth structure in Japan. Okay, then. Let's see what are the function of phasing. I'd like to explain why the GRS structure is stable against the traffic load or seismic load. So in order to explain the stability and the advantage of GRS structure, we have to correctly understand why the phasing, what is the function of phasing. So of course there's a three main element for reinforced soil wall: soil and reinforcement and phasing. It is same GRS retaining wall or Taylor method. This is the main element. So the question is, what is the function of phasing? Why we need a phasing? Why the phasing exists? What is the role of phasing? That is the question, and I know I sometimes I feel that engineer misunderstand the function of phasing. So the question is, some engineer said that earth pressure does not act on the phasing. So this is because reinforcement such as geosynthetic or metal strip reduce the earth pressure. And phasing is used only for covering the backfill, preventing from local erosion, local failure, and ultraviolet wave. So do you think such comment from some researcher is true or false? That is a question today. So I think some researcher know correctly what is the function of phasing, but I'm afraid that some engineer today, some audience doesn't know correctly about what is the function of phasing. Let's see the Henri Vidal, how he evaluates the function of phasing. Henri Vidal is a very famous engineer who invented the Taylor-Arme method. And in his paper, International Conference of 1978, he told that we should not have any need for phasing. And the phasing retained the grains located near the exterior between the two layers of reinforcement. So it corresponds to a very local problem and is not important. That is the opinion from Henri Vidal, who invented the Taylor method. So it seems that the function of phasing is not important. So let's see the initial stage of Taylor method, as it is different from the current style. At the beginning, at the initial stage, Taylor method used the U-shaped metal skin as a phasing like this. And the it is showing the patent at 1963. At the beginning, they used such kind of U-shaped phasing. And Henri Vidal, I found another literature about Henri Vidal lecture at 1965, some keynote lecture chaired by Professor Kako. And he told that this extremely interesting result is physically observed on the reduced model. It seems that he performed a model test. And he said stresses in earth trapped inside the skin element here are satisfied and ranking equilibrium. And the phasing must therefore have the particular property of being locally resistant enough while being flexible as a whole. So it means that Henri Vidal understands that there is some mechanical equilibrium around the phasing, but he thought that it needs a local resistance for achieve such mechanical equilibrium. But he thought that as a whole, the phasing is enough to being flexible. That it seems that Henri Vidal thought in that way. And I found another literature at LCPC LCPC is the former name of the if star who invented the Taylor method. At the beginning, they perform many model tests like this using the aluminum rod. And you can see the U-shape metals model like this. And it seems that they are doing some vertical loading test for this model. But I cannot find any data of the earth pressure measurement. And I think the earth pressure is acting on the facing, but it was not reported in the literature. And let's see another French engineer who also invented the Taylor method named Schlosser, who is a professor of the École Nationale de Ponts et Chaussées, who collaboratively invented the Taylor method with Henri Vidal. And in his literature, he made a very interesting comment. He said, increasing the stiffness of the wall facing, it decreases the deformation of the wall, while increasing the lateral pressure applied to the facing. That is what he found through his model test. So for the left figure show the lateral facing pressure, earth pressure, and the wall height. And he changed the facing rigidity from rigid, medium, and flexible. And the red line showing the earth pressure acting on the rigid facing, he found that earth pressure increases compared to the blue line, which is observed for the flexible facing. And the right figure showing the tensile stress in the reinforcement and the distance to the facing. So he found that tensile force increases with a compaction, and you can see the tensile force is higher at the vicinity of the facing. So that is what he found. So if we follow his Professor Schlosser's experiment, the function of facing is very important. So it means tensile force become large as the connection with the wall, and the wall resist earth pressure. And of course, it means the wall restrain the soil. So let's see the available tensile force, which is very important for the stability of the reinforced soil structure when the connection strength is 0 or the facing is very flexible. Then if the connection strength is 0 and the facing is very flexible, we cannot expect any earth pressure at the wall faces because it is flexible. So the earth pressure cannot act on the facing. Then, in that case, the low tensile force in the reinforcement, in particular at the low wall level, because the less earth pressure, so the tensile force becomes smaller. Then the active zone the confining pressure become very low. Therefore, then the low confining pressure induce a low soil strength. Then the stability of the wall become very small. So that is what happens when the connection strength is 0 or the facing is very flexible. But on the other hand, let's see what we have, what the kind of available tensile force when the facing is rigid enough or connection strength is high enough. First of all, we can expect that high earth pressure at the wall face like this because it is firmly connected and the facing have a high rigidity. And then high tensile force in the reinforcement can be expected. So in that case, in the active zone, the confining pressure become high, so the strength of the soil become high because the strength and the stiffness of the soil increases by the increase of the confining pressure, and then we can expect high stability of the wall. So it means that the rigidity of the facing is very important, and the reinforcement should be connected to the facing firmly. But when we see the development of Taylor-May, as I told you, at the initial stage, they used the U-shaped metallic element. But as you know, in the current style, they no longer use the U-shaped metallic element, but using the facing panel, which is concrete facing panel, where the rigidity is very high. So I think they have a very positive effect by using the rigid facing panel. then I try to find the reason why they changed the U-shape metallic element to the concrete facing panel. But in the literature, Andy Vidal said it is only the reason is only the appearance. It is because it looks very attractive. And Shirosha said it become possible for the various architecture possibility. And unfortunately, I couldn't find any explanation about earth pressure effect, which stabilized the backfill soil. But I believe that such effect, such positive effect also exists by changing from the U-shape skin element to the concrete facing panel, mobilize higher tensile force in the reinforcement. So let's go back to the answer to the question. Is that the facing is an important and essential structural component, and the earth pressure at the facing should be high enough to provide sufficient confining pressure to the backfill. That is the answer. So we have to understand that the importance of the facing rigidity and the facing reinforced connection, and it should not be overlooked. And there's another problem of using the discrete panel facing. This shows some example of the collapse of discrete panel in US. When there's some local failure caused by some erosion of a skull or some other reason, local failure may quickly result into the collapse of the whole wall. But and this is another example. But such kind of progressive failure, which sometimes happen in the discrete panel, doesn't happen if we use the rigid, continuous rigid facing. So local failure in a limited number of discrete panel caused by skull wall of the supporting ground resulted into the failure of the whole wall. That is the problem of using the discrete panel facing. And this is the advantage of using the continuous rigid facing. And there's another problem during earthquake using the discrete panel facing. This picture was taken after the 1999 earthquake in Taiwan. And we observed that the local failure in the modular block, it is a modular block facing due to the connection failure between blocks and geogrid reinforcement resulted into the failure of the whole wall. So in terms of the seismic stability, it seems that it's better to use the continuous rigid facing. But another problem is how to attach the geogrid to the full height rigid facing. As I explained, the connection between the rigid facing and the geosynthetic is very important. But the problem is how to attach the geogrid to the full height rigid facing. And the Schlosser again told that he told that some problem using the geotech style. He tried to use it at LCPC in France from 1971, but he faced with several problems. One is utilization of geotech style has been rather limited because of their high deformability. And another problem is related to the facing problem. It should be solved, he said. It means that the difficulty in construction and the method for attaching the geogrid to the facing panel. So that is what Schlosser found that problem. The problem which was found by Schlosser. There are two problems. It is high deformability of the geotech style and how to achieve the connection between the geogrid and the facing. But it seems not difficult to achieve the strong facing reinforcement connection by constructing the wall before backfill. This picture show that the engineer constructed the wall first, and the geogrid have already prepared and connected to the facing. And some work are doing the earthwork and doing the compaction. If we look at this picture, we thought that it is not difficult to achieve the strong facing reinforcement connection. However, there are critical problem of this construction procedure. I would like to explain what is the critical problem of this procedure. First of all, when we try to construct the wall facing wall first, we need for a propping to support the wall. And after that, we start earthwork. So first problem is that it is difficult to compact the backfill immediately behind the facing. But this position, the active zone, is very important. So we have to compact this area sufficiently. But if the wall exists first, it becomes difficult to compact sufficiently. And during the compaction, damage to the connection due to the relative settlement between the facing and the backfill occurs. That is the second problem. And the third problem is no tensile strains before removing the propping. Of course, the wall is fixed, so no tensile strain, no active tensile force was mobilized in the geogrid. So when we remove the propping, there is some uncontrolled movement upon the removable of the propping. So that is a problem when we construct the wall first in order to achieve the firm connection between the geogrid and the wall facing. So this and the Japanese engineer tried to find a solution how to solve this problem. They found that this problem can be solved by the staged construction procedure. That is one of the main characteristic of the 3R method. Staged construction means not constructing the wall first, but constructing the backfill first. I would like to explain the procedure of this staged construction. So this is a standard stage construction procedure for such walls. So first, a small foundation for the facing is constructed, just a small one. And then a wall having a wrap around wall face is constructed with the help of gravel-filled bags placed at the shoulder of each soil layer. And distribute the soil backfill material here and do the compaction enough. So we have to, of course, we have to do the good compaction of the backfill. But the important point is at this stage, there's no rigid facing during the backfill compaction. There's no backfill here. And we repeated this earthwork and placed the wrap around gravel backfill and arranged the geogrid in this way. So by repeating this construction procedure, we can construct the reinforced soil backfill like this. So this is the complete of the wrap around wall. And important thing is that we can wait in this stage if needed. Because sometimes the compression happens in the backfill, or sometimes there's a compression in the ground due to the consolidation. So if such compression behavior is predicted, we can wait by this stage, not constructing the wall surface. And after the sufficient compression of backfill and ground, and then we can construct the wall surface facing after it. So here we use the cast-in-place concrete for the RC facing, and this is showing the structural detail of the cast-in-place RC facing. For first, of course, we need a steel reinforcement, this black line, and we use the concrete formwork only at the front, and not using the formwork in between the RC facing and the soil bag. Then when we put the cast-in-place concrete, fresh concrete entered the gravel bags here through the aperture of the geogrid bag here. So then it becomes possible the facing and geogrid reinforcement become firmly connected to each other. So we can achieve such firmly connection between the facing and the geogrid by using this staged construction. So this is one of the breakthrough of this method, 3R method. And this is the typical one of the example of the GRS retaining wall supporting a very busy urban train in Tokyo, constructed around 1997 and 1998, supporting the Yamanote line, which is a very busy line, which I'm every day I'm using. And in front of the wall, there's another very busy line named the Chuo line. This picture was taken during the construction, before the construction of the wall facing. And this is after the wall facing, and the passenger is 6.4 million per day. Then what is important is that you can see the track center on the backfill is very close to the facing. Only it have only 1.5 meters or something, so it's very close. The reason why it become possible to construct in that way is that the facing is a rigid facing, is very rigid, and it is connected to the geogrid family. And on the other hand, this is an example of the Taylor-Arme method for the TGV in France, which is constructed around 2012 and 13. And you can see the rail center is constructed far from the wall, avoiding the traffic load acting on the wall directly. I heard the reason why they need 6.6 meters from the wall, and the French engineer told that it is necessary to avoid the traffic load directly acting on the wall. So this is due to the uncontinuous facing because the Taylor-Arme method using a discrete panel. So this summarizes the development of the facing type for both Taylor-Arme method and the 3R method. In the initial stage, both of the methods use a soft facing, like a metal skin, and at the beginning of the 3R method, they doesn't use the facing. But through some experiment or other research, they realized that it is better to use the hard facing panel for Taylor-Arme or full height rigid facing. So the understanding from some engineer, facing is not important or disadvantage of geosynthetic is misunderstanding, and this problem was already solved was already solved. There is a certain effect of facing, and these disadvantages have already been overcome. And there is another positive effect by using the full height rigid facing. By using the full height rigid facing, it becomes possible to support the foundation of the superstructure, such as electric poles, a noise barrier, and the bridge girder, etc., on the top of the wall. Usually, we construct such kind of electric pole like this, which is different from the wall, but thanks to the very high rigidity of the wall surface, we can directly put such kind of electric pole directly on the top of the wall. That is one of the positive effects by using the full height rigid facing. And another positive effect is the seismic stability. We experienced a huge earthquake at 1995 called Kobe earthquake, which is the west part of Japan, and the 3R method was 3R wall existed at that site. At 1992, this is taken after the completion, after the construction, and this picture was taken a week after the 1995. And you can see the houses around the wall was critically collapsed, but the wall survived. So we found that the GRS retaining wall performed very well during severe earthquake. But at that time, the reason of this high seismic stability of GRS retaining wall was not clear. So that is the fourth topic of today's presentation: seismic stability of the GRS retaining wall. Okay, how many minutes remains? Only 20 minutes. Okay, I have to hurry up. Oh, I have not yet half this. Okay, seismic stability of GRS retaining wall. So this picture shows the main force acting on the wall during facing. For the conventional type retaining wall, inertial force and the seismic earth pressure act on the wall as an external force, and this wall resists this external force, the subsoil reaction force. But in case of GRS retaining wall, they resist by tensile force and a little subsoil reaction force. And I performed many model tests and measure these forces. And I prepared 6 different model, conventional type retaining wall and reinforced GRS type. And this model was subjected to the irregular shaking table test. I increased the acceleration level gradually. And it showed the failure of the wall, and you can see some clear failure plane in the backfill, and it is showing the maximum acceleration when this retaining wall reached to the failure. So you can see that the maximum acceleration, for example, this is 1,000 or 1,100 gauss. It is a huge acceleration, but it is very large, but compared to the conventional type retaining wall. And this figure shows the displacement measured at the top of the retaining wall to the seismic coefficient. So in case of the conventional retaining wall, once the displacement happens, then the displacement increases rapidly. On the other hand, for the GRS retaining wall, it shows a ductile behavior. So this different degree of ductility is caused by the different resistant mechanism. I would like to explain in detail about it. For in case of conventional type retaining wall, it resists by the subsoil reaction force. It was measured at 4 different points. And this figure shows the relationship between the normal stress at the bottom surface, subsoil reaction force, and the top displacement. And at the first step, stress concentration at the top of footing was observed. At the top of the footing, the subsoil reaction force increases. But once the loss of bearing capacity occurs, then the top displacement increases rapidly. That is what we observed for the conventional retaining wall. And the reason of the brittle behavior of the conventional type is coming from this local failure due to the loss of bearing capacity. On the other hand, for the GRS retaining wall, this shows the relation between the tensile force and the top displacement, but such tensile force didn't decrease in like a bearing capacity. So that is why it showed that ductile behavior compared to the conventional type retaining wall. So the tensile force increased with the top displacement, and this explained the ductile behavior of the reinforced soil retaining wall. So that is what we found through the shaking table model test. So in the first chapter, I would like to summarize the advantage of GRS retaining wall, advantage of GRS retaining wall in construction. I would like to compare the advantage of this retaining wall when we are going to construct this GRS retaining wall on the extremely weak ground, relatively weak ground, and a good ground. And in case of extremely weak ground, subsoil condition, if we use the conventional type retaining wall, we need a pile foundation and ground improvement. But if we use a GRS retaining wall, only the ground improvement is needed. We don't have to construct a pile foundation. So that is one of the advantage. And when we are constructing this wall on the relatively weak ground condition, in case of conventional retaining wall, we still need a pile foundation. But in case of GRS retaining wall, we can construct RC facing directly on the relatively weak ground, because we can construct RC facing after the settlement finished, thanks to the stage construction. And in case of good subsoil condition, of course, we don't need any pile foundation or soil improvement. But in case of conventional retaining wall, the retaining wall resists against the earth pressure by the subsoil reaction force at the bottom footing. So we need a large footing. Large footing is required. But in case of GRS retaining wall, we don't need a large footing because the tensile force resists against the earth pressure or the inertial force in case of earthquake. So I would like to compare the cost, construction cost in these two cases when we are constructing the retaining wall on the relatively weak ground, the good ground. And this is a comparison. In case this one is in case of the 20-meter thick relatively soft ground. In case of the cantilever type retaining wall, we need a pile foundation. But in case of the 3R method, we don't need a pile foundation. So you can see with the construction cost, if we say that this construction cost of this method is 1, then the construction cost of this 3R method becomes 0.28. So more than 70% of cost reduction can be realized by using the conventional, by using the 3R method. And of course, maintenance cost is not so much different, but the total cost, total life cycle cost decreases. Yes, I forgot to tell you that this trial design was done by considering the seismic action. Seismic coefficient is 0.2, which is level 1 earthquake in Japan. So That is the history and of the development of GRS retaining wall. But in this chapter 6, I would like to explain about the GRS to the bridge abutment, not the retaining wall, but the bridge abutment, which was developed through between 2000 and 2010. And this schematically showing the railway structure, tunnel, embankment, box culvert, and bridge abutment, and viaduct. But very often, the differential settlement occurs just behind the bridge abutment or box culvert. We usually call this area as transition zone. And this transition zone is often suffering from the differential substance, which require frequent maintenance work. This is because the embankment or box culvert, when they are constructed on the relatively soft ground, it is supported by the foundation, but the supporting mechanism is different between the embankment and the bridge abutment. So such kind of relative settlement often occurs at the bridge behind the bridge abutment or box culvert, and maintenance and reinforcement of existing embankment at transition zone are still a major technical issue in Japan. But I heard that it is not only the issue in Japan, but such problem at transition zone exists all over the world, just behind the concrete structures. And another problem at this transition zone is that it becomes the weak point after the earthquake. For example, at 1995 Kobe earthquake or 2011 Tohoku earthquake, you can see the embankment backfill behind the bridge abutment like this was settled. Large settlement was observed. So that is another problem. So in the design standard for the railway structures at 1967, railway engineer thought that it is better to use the well-graded gravel in order to avoid such differential settlement behind the bridge abutment. They in the standard they used the well-graded gravel in the upside-down triangle shape, but there is another problem by using this well-graded gravel. The problem is sudden change of the support rigidity because the train passes on this embankment and the bridge abutment. But if we if we use the well-graded gravel in this shape, upside down triangle shape, then the sudden change of the support rigidity happens. So in the standard of 1978, they changed the shape of the well-graded gravel from a triangle shape to the trapezoidal shape in order to reduce the sudden change of the support rigidity, because embankment rigidity gradually increased here, and the track will supported by the bridge. But we thought that there is still some problem by using this well-graded gravel in the trapezoidal shape, especially during the earthquake. So we thought that isn't it better to apply the GRS method to that transition zone. So we perform many model tests, static loading tests, and shaking table model tests, and numerical analysis. And this video is the example of the shaking table test of the bridge abutment. The left one is a conventional type using the well-graded gravel, and the sinusoidal wave is 450 Gauss. And at the end, you can see the settlement just behind the bridge abutment. But when if we use a geosynthetic, and this zone was constructed by the cement mixed soil, and the geosynthetic is connected to the bridge girder, the seismic stability of the bridge abutment. Oh, this is hiding the most important point, sorry. Sorry. So what I want to tell you is that the settlement just behind the bridge abutment is very, very less, even though the input acceleration become double, okay? So this showing the time history through the model test. So this showing the base acceleration. Please look at this point A. So when the inertial force is acting outward, it means that the inertial force is acting in a dangerous direction, point A. You can see the subsoil reaction force is increasing, and pointer, and the reinforcement tensile force is increasing. So it means that the resistant force is increasing when the inertial force is acting forward. But you can see the seismic earth pressure is decreasing here. Okay, degreasing. So that is what we found through the model test. It means that if we construct this part, this green part with the very stable material and reinforced with the geosynthetic, the seismic earth pressure doesn't act on the bridge abutment. That is what we found. So this is a summary. Under dynamically active condition, point A, the resistance component increases. The red line, resistance component increases, but seismic earth pressure didn't decrease. So based on this model test and other numerical analysis or static model test, we proposed using the method of GRS retaining wall to the bridge girder. Very simply placing the girder directly on the top of the facing and using the cement mix backfill behind the facing like this. And we applied this GRS bridge abutment for the permanent structure of the Shinkansen in the third generation at the Kyushu Island. And the height of the bridge abutment is 12.5 meters. And this picture taken after the construction, and 20% of cost reduction was realized by applying the GRS bridge abutment. And during this showed the stage construction. Of course, it was stage construction was also applied to this method. First, we construct the cement, the backfill reinforced by the geosynthetic, and after that, constructing the facing, and finally putting the girder on it. And by this method, it is possible to avoid the relative displacement between the embankment and the bridge abutment by this stage construction. And we compare the construction cost between the conventional type and the GRS abutment. This left one is the actually constructed, and the right one is a conventional type. If the conventional method, cantilever type bridge abutment was applied to the site, you can see if we try to construct by the conventional type bridge abutment, that the volume of the bridge abutment become very large compared to the GRS abutment. So it is showing the construction cost. The cost for reinforced concrete become more than the double by using the construction. But of course, in this GRS construction, we use a lot of geosynthetic, so the cost for reinforcement increases, but total cost decreases. So it means that we achieve the low construction cost and high seismic stability. So low construction, high seismic stability. So it becomes the major bridge abutment construction method in Japan. And however, this was the first application of GRS abutment. So we tested the stability of this bridge abutment by applying a lateral load directly to this abutment to ensure the stability and the connection strengths between the abutment and the geosynthetic. So we had to apply the load horizontally to the bridge abutment. So first we have to do is that connecting the two, combining the two bridge pier for the reaction force. First we combine two bridge pier, and after this we put the bridge abutment and this combined pier each other. So this part is the reaction force, and we are looking at the displacement of the bridge abutment. So this is the test result showing the lateral load and the lateral displacement. And you can see this is a displacement of Pier 5 and displacement of the GRS bridge abutment measured here. So what we confirmed is that the GRS bridge abutment was much more stable against the lateral load than the combined two piers without any signs of separation of facing, full height rigid facing from the geogrid reinforced backfill. That is what we found. It means that one bridge abutment was more stable than the two combined bridge pier. And this showed the displacement of the bridge abutment and the crack when the lateral load was 4,000 kilonewton, 500 ton maximum. And when we applied 400 ton lateral loading, the maximum the displacement was 15.52 millimeter, but the residual displacement is only 10 millimeter. So, and we don't, we confirm the firm connection between the geotech style and the bridge abutment. So that is what we found from the full height bridge abutment, lateral loading test of the full height bridge abutment. Okay, then, only 5 minutes remain. 5 minutes, okay. Chapter 7, okay, I have to finish in 5, but that's chapter 7 is also very important, but I have to rush and finish this chapter because I'm going to like to introduce a design standard of the Japanese railway related to GRS structures. Okay, we published the design standard for the retaining structure 2012, which is based on the performance-based design. Performance-based design. It means that the performance of the conventional type retaining wall or bridge abutment or GRS type retaining wall or bridge abutment can be verified by using the equivalent index. So the question is the performance-based design necessary for our structure? So that was the problem. But I think I have to skip this topic by the time. Okay, but we need a performance-based design because railway is supported by inline structures such as embankment and viaduct tunnel. So the performance of the railway inline structures should be verified with the identical requirements. So when we use a specification-based design, which is a conventional design method, it is difficult. A problem is specification is not directly linked to the required performance. And the performance of the R structure is difficult to compare with the other structure type. So that was the problem. So in Japan, we revised the design standard to the performance-based design. And it can deal with a respective condition and can adapt the newly developed technique according to the required performance. So in the current design standard, we can compare the performance between the GRS structures and conventional structures using the equivalent performance index. And this is the content of the design standard. I have to skip. It's showing the required performance of the all structures, safety and stability, serviceability and restorability. And in chapter 5, what kind of backfill material have to be used. It is clearly written here. And yes, here. And the important is reinforcement, geotech style. It's written as reinforcement shall be those whose quality has been ascertained, and their characteristic value and design value shall be appropriately determined. Okay, and we need several correction factors, such as material correction factor or material factors. But we use a different factor based on the action we use in the design: general action, a variable action, or seismic action. And there's another reduction factors have to be used for the geosynthetic, for reduction factor for considering alkali resistance or damage during construction or creep or momentary load or train load. And it is named alpha 1, 2, 3, 4, 5. And we use these 5 different reduction factors depending on the action which we considered in design, like permanent action or variable action or seismic actions. And in case of retaining wall, of course, we have to evaluate the internal stability and external stability. And for the seismic design, we have to calculate the residual displacement caused by the large earthquake. And we have to compare the calculated displacement with the allowable displacement. Okay. And we use a Newmark method for obtaining the displacement. So, and allowable displacement is also written very clearly in this design standard. We define the deformation level 1, 2, 3, 4, and the deformation level 1 is almost no deformation, 2 is some deformation, 3 is large residual deformation, and the allowable settlement of the embankment is different between the slab track and the ballasted track. For example, in case of the large earthquake, we allow only 5 centimeters for slab track or 20 centimeters for the ballast track. Such kind of allowable settlement is clearly written in the design standard. And it also shows the structural detail of the minimum length of the reinforcement and arrangement of the reinforcement like this. And some other structural detail of the reinforcement joint or foundation for reinforced wall facing and embedded depths. And a temporary holding at the wall face, such as the soil bags, cross section of soil bags and front view. And we recently often use a welded steel fabric for the construction. And this is a picture how we use such a welded steel fabric, and it's showing the construction work procedure in case of the widening of the existing embankment, construction of the foundation for the facing, and arranging the first geometric style layer together with temporal wall first holding, and backfill and compaction like this. And complete of the construction of the reinforced soil backfill. And of course, at this stage, there's no wall facing. And after that, constructing the facing like this. And there is another technical guideline which is published from the Austrian Association like this. So this technical guideline is now available on the website. So if you are interested in such a design procedure and the construction procedure of this 3R method, please make an access to this site written below. And the final topic is just overview of the recent application of the new Shinkansen line in Hokkaido Shinkansen. And I would like to show this one picture. It looks like concrete structure, which is taken at 2013. It all looks like concrete structures, but actually all structure made by the GRS structures, such as GRS retaining wall, GRS abutment, and GRS integral bridge, which will be precisely explained by Professor Tatsuoka after me. So it means that inside this concrete facing, there is a soil and geosynthetic. This is another example of the overseas project in Vietnam. The length is 1.5 kilometer and height is maximum 5.7 meter for the 3R method retaining wall. And this is taken at Vietnam, the engineer constructing the wall facing after they complete the constructing the backfill with the geogrid. Another overseas project is Indonesia, the Jakarta, constructing the roll stock. And this is showing the construction of the construction procedure starting from here, 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 and complete. So that is another example at Indonesia. So this is the final slide for my presentation. Conclusion is GRS retaining wall with full height rigid facing has been constructed as important permanent structure, mainly for railways, including high-speed railway, Shinkansen in Japanese. And this is due to its cost effectiveness by high performance and low life cycle cost. And there are two key aspects of this technique. Important point is full height rigid facing and connected firmly to geosynthetic and stage construction. We construct the backfill first and after we construct the wall. And this technique was applied to the bridge abutment, not only the retaining wall, but it is applied to bridge abutment and has already become a very common technique in Japan. And this method has recently been applied to in many overseas railway projects. Okay, thank you for delay for a few minutes. Thank you for your kind attention. And this is picture at University of Tokyo, and I'm working in this building. So if you have a chance, please visit my university. So thank you very much. ありがとうございます。